So what we saw in the last video is that a normal distribution, which is what that curve we drew in the last example for the continuous variable, a normal distribution is a continuous probability distribution for a continuous random variable x. Now, just that first sentence alone can sound like a lot, but don't be overwhelmed. That is exactly what we just talked about here, is that this curve that I'm now outlining in red, this is what we're going to be talking about in this lesson, is the equivalent of this probability distribution, which was for a discrete random variable. Now we're doing it for a continuous random variable. And we talked about the difference between those things. The graph of the normal distribution, that same curve that I outlined in red, the same curve that we see down here, is called the normal curve. And now we're going to talk about some of the properties of a normal distribution. The first property is that the mean, median, and mode are always equal. The second property is that the normal curve is bell-shaped and it is symmetric about the mean. So what that means, this being symmetric about the mean, means that I could go in and draw a vertical line that cuts this bell curve in half, and that vertical line remember, for context, this horizontal axis down here that I'm doing in orange, remember that represents the values of the continuous random variable. Remember we talked about that up here? Those represents the values of the continuous random variable. Where I would be splitting that curve in half would be happening at the mean, which is mu. It would be happening in the middle at the mean. The third property is that the total area under this curve is 1. And that does make sense and should make sense to us because remember we were drawing the similarities between the probability distribution for the discrete random variable and the one for the continuous random variable. And we do know that all 5 of these values here must add up to 1 in order for this to be a probability distribution. And if on the continuous random variable side, we're saying the area is represented, we're saying that the probability is represented by the area under the curve, then all that area under the curve needs to add up to 1. And that is very important. I won't write that here. I'll put that more up here. That is very important. We will use the fact that the total area under the curve needs to be 1 in a lot of the examples that we do. So just a quick little preview. The idea behind that is that if I were to chop the curve right here, ignore the blue line for now, but if I were to chop the curve right here and tell you that 30% of the data is to the left, then that means there has to be 70% of the data to the right. Because when I add the total area under the curve, adding those two, I should get 1. Okay, so that's the idea between how we will use that fact that the total area under that curve is 1. The fourth fact is more of like a very mathematical fact. We won't use it very much as we do our calculations or as we actually look at problems, but it is that this curve approaches but never touches the x-axis. So I know it does look like on this graph here that it touches the x-axis, but the idea is that the curve kind of just gets closer and closer and closer and closer and closer to the x-axis, but never actually touches it. And if you're familiar with other math courses like maybe pre-calc or calculus, the idea of asymptotes kind of have the same things going on there. It's getting very close to the x-axis but never touching it as it gets further and further away from the mean. So as we get further and further away from the mean, we get very close to but never touch the x-axis. The next idea talks about these little tick marks that are down here at the bottom along that axis there. Remember, we said that this is spread out in the middle, distributed evenly in the middle around the mean. And what's measuring how spaced out the data is the standard deviation. So we say that between mu minus the standard deviation, so whatever the mean is, move a standard deviation to the left, and whatever the mean is, move a standard deviation to the right. So between these two here, that the graph is curved downward. The normal curve is curved downward between those 2 points right there. Those 2 points right there are called inflection points. That's where most of the data is concentrated. Most of the data is concentrated between those two inflection points. And this does tie in kind of like if you're thinking about the empirical rule right now. After we get past those inflection points, the rest of the graph, and remember on that red piece, the graph is curved downward. After you pass those inflection points, the graph is curved upward. So I kind of flared it out when I really shouldn't be doing that. But the graph is curved upward on those two purple pieces. It's kind of, if I were to extend it out, you can kind of see that's cupping up. Like I could, in the purple pieces, kind of imagine if like it was raining, the purple pieces could collect water, but the red pieces, the water would just roll right off of it. That's what I mean by pointing upward and pointing downward, okay? So I'm going to put that into words right now for our final property of the normal distribution. So I wrote that between mu minus sigma and mu plus sigma, and this is a sigma for the standard deviation, between those two values, the graph is curved downward. Past those values, what I outlined in purple, the graph is curved upward, and those values are called inflection points, where the graph is changing from moving upward to downward. So if we're able to look at a graph and kind of pinpoint where that inflection point is, we should be able to tell what the standard deviation is, because the inflection points are one standard deviation away from the mean. One standard dev away from the mean. We should also be able to look at a graph and tell about what the mean is, because the mean should be smack dab in the center. Because remember, the mean, median, and mode are all the same here. The mean should be smack dab in the center of that curve. So now I hope it makes a little bit more sense why I kind of modeled this like this. Because what a normal curve means, when things happen normally, most people fall in the middle. When things happen normally, most people fall in the middle. Things that are normally distributed, they have their mean in the middle, and most of the data is happening towards that also in the middle. A lot of things follow normal distributions, like the blood pressure of humans. Most humans have an average blood pressure. You may be a little bit above average in this area. You may be a little bit below average in that area, but it's highly unlikely that you're really, really, really low blood pressure. It's a very low probability that you have a very, 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 very low blood pressure, or a very low probability that you have a very, very, very high blood pressure, that you're all the way to the right of the mean. Another thing that follows a normal distribution, say, is the cost of houses. If you look at a certain area, most houses are going to cost around the average price. And they may cost a little bit more than average. They may cost a little bit less than average, but most of the data is going to fall right there in the middle. What is going to be less likely is that you have a lot of really expensive homes, and what's going to be less likely is that you have a lot of really cheap homes. Most of your data is going to fall in the middle. That's what it means for something to be normally distributed, following this bell-shaped symmetric curve. And now we're going to look at some examples. Before we went on to look at some examples, I wanted to talk briefly about what a probability density function is. We have already seen from lesson 12 that a discrete probability distribution can be modeled. We can graph that using a histogram. So here's an example of a discrete probability distribution that we made, and we graphed it using a histogram. Now, what we're learning about in this lesson is how a continuous probability distribution can be graphed. And we've already seen an example that it can be graphed with a normal curve. We've already seen an example that it can be graphed with a normal curve. But more generally, a normal curve is a specific example of a probability density function. So a probability density function is a function that models the probability distribution for any continuous variable. And the normal curve is just an example of that. We're not going to talk too much about PDFs in general. This is abbreviated PDF for probability density function. We're going to focus mostly on normal curves because the normal curve is the most important type of PDF. But I just wanted you to know that that's what the normal curve is, an example of a PDF. We will look at other PDFs in the course. Like eventually we'll talk about the t-distribution, and eventually we'll talk about the chi-squared distribution, but those are just other examples of PDFs. The two requirements of a PDF is that the total area under the curve must be 1. We knew that. We talked about that already. It's the same way that in a discrete probability distribution, all of the probabilities have to add up to 1. And the function can never be negative, which also makes sense because if a PDF is modeling probability, we should not have a negative probability. All of our probabilities should be 0 or positive.